When we gaze up at the night sky, past the twinkling stars, beyond the swirling arms of our Milky Way galaxy, we're drawn to a question as old as human curiosity itself. What is the universe? And more provocatively, is there anything outside it? But before we can even begin to explore what might lie beyond, we must first ask, what do we actually mean by the universe? At first glance, the answer seems simple. The universe is everything, all matter, all energy, all space and time. But in science, and especially in cosmology, precision matters. And the word universe carries several nuanced meanings depending on context. Let's start with the most practical definition, the observable universe. This is the spherical region of space from which light has had time to reach us since the Big Bang, roughly 13.8 billion years ago. Because the universe has a finite age and light travels at a finite speed, there's a hard limit to how far we can see. That boundary lies about 46.5 billion light years away in every direction. Not because the universe is only that big, but because space itself has been expanding during the time light traveled toward us. So, the observable universe contains an estimated 2 trillion galaxies, each with billions or trillions of stars, plus dark matter, black holes, cosmic radiation, and the mysterious dark energy accelerating cosmic expansion. It's vast beyond everyday comprehension, but crucially, it's not necessarily the whole story. Now consider the entire universe, the totality of all that exists, whether we can observe it or not. Here's where things get tricky. If the universe is infinite, then it stretches forever in all directions, containing endless repetitions of galaxies, stars, and perhaps even versions of you reading this very sentence. In that case, there is no outside, because infinity has no edge. But what if the universe is finite? Could it have a boundary? Surprisingly, even a finite universe might not have an edge in the way we imagine. Think of the surface of a balloon. It's finite in area, yet you can travel forever in any direction without falling off. Similarly, our 3D universe could be closed and curved in a higher dimension, like the 3D analog of a sphere's 2D surface. In such a model, if you traveled in a perfectly straight line for long enough, ignoring expansion, you'd eventually return to your starting point. Again, no edge, no outside. This leads to a profound insight. Outside may be a meaningless concept. Why? Because space and time themselves are part of the universe. They didn't exist before the Big Bang or outside it because time and space began with it. Asking what's outside the universe might be like asking what's north of the North Pole. The framework we use to define location, direction, and existence simply doesn't apply. Still, some theories push the boundaries of this thinking. Take cosmic inflation, the leading theory of the universe's earliest moments. It proposes that a tiny patch of space-time underwent exponential expansion faster than light, creating the vast cosmos we see. But inflation may not have stopped everywhere at once. In some regions, it continues eternally, spawning pocket universes like bubbles in an infinite quantum foam. In this eternal inflation multiverse, our universe is just one bubble among countless others, each with its own laws of physics. In that scenario, is there an outside? Well, yes, but not empty space as we know it. Instead, there's a meta-universe or multiverse substrate, a seething, inflating quantum field where new universes constantly form. Yet even this outside is still part of a larger physical reality governed by overarching laws. So is it truly outside the universe, or just part of a bigger universe we haven't named yet? Philosophers have long wrestled with this ambiguity. Some argue that by definition, the universe includes all that is real, So if something exists, it's part of the universe, and the word outside becomes self-contradictory. Others suggest we should distinguish between our local cosmos and ultimate reality, allowing room for structures beyond our causal horizon. Then there's the radical idea proposed by physicist Max Tegmark, the mathematical universe hypothesis. He suggests that physical reality isn't just described by math, it is math. In this view, every mathematically consistent structure exists as a physical universe. Our universe is just one solution to cosmic equations. Outside, ours would be other mathematical structures, entirely disconnected realities with different dimensions, forces, or logics. But again, are these outside, or just other parts of a grander ensemble? Importantly, none of these ideas are currently testable in the traditional scientific sense. We cannot send a probe beyond the cosmic horizon. We cannot observe other bubble universes. At best, we look for subtle imprints like collisions between bubbles in the cosmic microwave background. But so far, evidence remains elusive. Imagine standing on a quiet beach at night, looking out over the ocean. The water stretches endlessly into darkness, yet you know your vision is limited. Fog, curvature of the Earth, and the faintness of distant lights all restrict how far you can see. Now, scale that feeling up to the entire cosmos. What you're experiencing is a metaphor for the observable universe. Our cosmic horizon, the ultimate limit of what we can ever witness. But here's the twist. This boundary isn't a wall in space. It's not like there's a sign that says, "End of universe. No trespassing." Instead, it's a limit imposed by time, light, and the expansion of space itself. Let's begin with time. The universe is approximately 13.8 billion years old. That means light, the fastest thing in existence, has only had 13.8 billion years to travel since the moment of the Big Bang. So, shouldn't the farthest object we can see be 13.8 billion light years away? Surprisingly, no. Because while light has been traveling toward us, space itself has been stretching. Think of two ants on an inflating balloon. Even if they aren't moving relative to the rubber, the distance between them grows as the balloon expands. Similarly, galaxies are carried apart by the expansion of space-time. As a result, the most distant objects whose light has just now reached us are actually about 46.5 billion light years away. That defines the radius of our observable universe, a sphere nearly 93 billion light years across. Within this bubble lies everything humanity has ever observed. Every galaxy mapped by the Hubble and James Webb Space Telescopes. Every quasar. Every whisper of the cosmic microwave background radiation. The afterglow of the Big Bang itself. It's estimated to contain 2 trillion galaxies, each hosting billions or even trillions of stars. And yet, this may be just a tiny fraction of the whole cosmos. Why? Because the universe likely extends far beyond what we can see, perhaps infinitely. There's no reason to believe that matter and energy suddenly stop at our horizon. In fact, observations of the cosmic microwave background suggest the universe is extremely uniform on large scales, implying that what lies beyond our view probably looks very much like what's inside it. But here's where things get deeply humbling. We will never see beyond this horizon. Not because our telescopes aren't powerful enough, but because of the laws of physics themselves. Due to the accelerating expansion of the universe, driven by the mysterious force we call dark energy, distant galaxies are receding from us faster and faster. Eventually, many will cross a threshold where their light can no longer reach us. Over trillions of years, future astronomers in the Milky Way may look out into a sky almost completely empty, devoid of other galaxies, with no trace of the Big Bang's echo. They would have no way of knowing they once lived in a rich, interconnected cosmos. This makes our current era uniquely privileged. We live at a time when the universe is still visible, when its history is written clearly in light that has journeyed across eons to meet our eyes. It's also worth noting that every observer has their own observable universe. An alien in a galaxy 10 billion light years away sees a different cosmic horizon, one that overlaps with ours but also includes regions forever hidden from Earth. There is no single center, no privileged viewpoint. The observable universe is personal, local, and temporary. Now, let's address a common misconception. Is the edge of the observable universe the edge of the Big Bang? Not quite. The Big Bang didn't happen at a single point in space. It happened everywhere at once. The entire universe, observable and beyond, was once compressed into an incredibly hot, dense state. So when we look deep into space, we're also looking back in time. The farthest light we detect, the cosmic microwave background, comes from a time just 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and photons to travel freely. Before that, the universe was opaque, a seething fog of plasma. We cannot see further back with light, but scientists use other tools, like gravitational waves or neutrino backgrounds, to probe even earlier moments, though these remain largely theoretical for now. So, what lies beyond our cosmic horizon? We don't know, and we may never know. It could be more galaxies, more stars, more cosmic structures stretching on forever. Or it could curve back on itself in a finite but unbounded geometry. Or it might connect to other universes in a vast multiverse. But crucially, none of those possibilities can affect us. No signal, no force, no information can cross from beyond the horizon into our observable realm. Those regions are causally disconnected from us, forever outside our influence and observation. This raises profound philosophical questions. If something exists but can never interact with us, not now, not ever, is it meaningful to say it exists in a scientific sense? Science relies on testability and evidence, and by definition, the unobservable universe lies beyond both. Yet, cosmologists still study it, not through direct observation, but through mathematical consistency and indirect clues. For example, patterns in the cosmic microwave background hint at the universe's overall geometry. If space were positively curved like a sphere, parallel lines would eventually converge. If negatively curved like a saddle, they diverge. Current data suggests the universe is flat to within a fraction of a percent, implying it could be infinite. But even if it's finite, remember, finite doesn't mean bounded. Just as Earth's surface is finite but has no edge, the universe could wrap around in higher dimensions we can't perceive. In the end, the observable universe is both a triumph and a limitation. It's a testament to human ingenuity that we've mapped the cosmos back to its infancy. Yet it also reminds us of our place, not at the center of all that is, but within a small, fleeting window of knowledge in an ocean of the unknown. As we move forward in this exploration into multiverses, higher dimensions, and the nature of nothingness, keep this horizon in mind. It's not a barrier to curiosity, but a beacon reminding us that wonder begins where certainty ends. Few questions stir the imagination quite like this. Is the universe finite, or does it go on forever? It's a question that straddles the line between science, philosophy, and even poetry. On one hand, infinity feels majestic, an endless expanse of stars, galaxies, and possibilities. On the other, finitude offers closure, structure, and perhaps even meaning. But what does modern cosmology actually tell us? The honest answer? We don't know for certain. But we have powerful tools, mathematics, observation, and theory that bring us remarkably close to an answer. Let's begin with what we can measure. Using data from missions like the Planck satellite, scientists have mapped the cosmic microwave background, CMB, the faint afterglow of the Big Bang, with extraordinary precision. Tiny temperature fluctuations in this radiation reveal the geometry of the universe on the largest scales. And here's the key insight. The shape of space tells us whether the universe is finite or infinite. According to Einstein's theory of general relativity, space can curve in three fundamental ways. Positive curvature, like the surface of a sphere. In this case, the universe would be finite but unbounded. Travel far enough in a straight line, and you'd loop back to your starting point, just as circumnavigating Earth brings you home. Negative curvature, like a saddle. Here, space would stretch infinitely, with parallel lines diverging forever point zero curvature, perfectly flat. In this scenario, space could still be infinite, or it could be finite if it has a non-trivial topology, like a video game screen where exiting one edge brings you back on the opposite side. So which is it? The data overwhelmingly points to flatness, to within 0.2% margin of error. That suggests the universe is either infinite or so vast that any curvature is too subtle for us to detect. But flatness alone doesn't settle the matter. Think of a piece of paper. It's flat, yet finite. Now imagine taping the edges together to form a cylinder. It's still geometrically flat, but now it's finite in one direction. Similarly, the universe could be flat yet finite if it has a wrapped topology like a 3D torus, a cosmic donut. In such a universe, light could circumnavigate space, and we might see repeating patterns in the sky, ghost images of our own galaxy in the distant past. Astronomers have searched for these repeating signatures in the CMB. So far, no evidence has been found. If the universe is finite and wrapped, it must be larger than our observable horizon, at least 500 billion light-years across, possibly much more. That means even if it's finite, it's so enormous that for all practical purposes, it might as well be infinite. Now consider the implications of each possibility. If the universe is infinite, then somewhere out there, beyond our horizon, there could be another Earth, another you. In fact, in an infinite cosmos with finite possible particle arrangements, exact copies of you must exist, reading this very sentence over and over again in an endless cosmic repetition. It's a mind-bending consequence of infinity, rooted not in speculation, but in probability. But infinity also brings paradoxes. An infinite universe contains infinite matter, infinite energy, infinite suffering, and infinite joy. It challenges our notions of uniqueness and meaning. As physicist J. Richard Gott once said, in an infinite universe, everything that can happen does happen an infinite number of times. On the other hand, if the universe is finite, it offers a kind of cosmic intimacy. There's a totality to existence, a complete story, however vast. Some find comfort in that. A finite universe might also imply a deeper symmetry or design, though science remains neutral on such interpretations. Importantly, finiteness doesn't require an edge. As we've noted before, a finite universe can be closed in on itself, like the 3D surface of a 4D hypersphere. You'd never hit a wall. You just keep going, eventually returning home. This model aligns with certain solutions to Einstein's equations and was long favored by cosmologists before precision data leaned toward flatness. But here's another twist. Even if the entire universe is finite, it may still be growing. The Big Bang wasn't an explosion into space. It was the rapid expansion of space itself. So a finite universe can expand forever without needing outside room to grow into. It's like inflating a balloon. The surface gets bigger, but it doesn't need to expand into anything else. And what about the future? Could the universe stop expanding and collapse back in a big crunch, implying finitude in time as well as space? Current evidence says no. Observations of distant supernovae and the CMB confirm that cosmic expansion is accelerating, driven by dark energy. Unless dark energy behaves in unexpected ways, the universe will likely expand forever, whether finite or infinite. So where does that leave us? We have strong observational evidence that the universe is spatially flat and extremely large. So large that if it's finite, it dwarfs our observable patch by orders of magnitude. We have no proof of repetition, no signs of wrapping, and no detected curvature. By the principle of Occam's razor, many scientists lean toward an infinite universe as the simplest explanation consistent with data. But, and this is crucial, science cannot prove infinity. You can't measure infinity. You can only say, as far as we can see, it keeps going. Infinity remains a model, not a confirmed fact. Philosophically, the question also touches on human limits. Our brains evolved to navigate savannas, not space-time manifolds. We struggle to truly grasp either absolute nothingness or true infinity. Perhaps the universe doesn't care about our intuitions. Yet the search continues. Future telescopes, gravitational wave observatories, and quantum gravity theories may one day reveal subtle topological clues, like matching circles in the CMB or anomalies in large-scale structure, that could finally tell us whether space closes in on itself. Until then, we stand at the edge of knowledge, gazing into the unknown. Whether the cosmos is finite or infinite, one thing is certain. It is far grander than we ever imagined. And in that mystery lies not ignorance, but wonder. For centuries, humanity believed Earth was the center of existence. Then we learned we orbit an ordinary star. Then we discovered our galaxy is just one among trillions. Now, some of the most respected physicists in the world propose an even more radical idea. Our entire universe might be just one of countless others, part of a vast, possibly infinite multiverse. But what does that really mean? And is it science or speculation? Let's begin by clarifying, multiverse isn't a single theory. It's a collection of distinct concepts that arise naturally from well-established physics, though each remains unproven. There are at least 4 major types of multiverses, each born from different lines of reasoning. The most scientifically grounded version comes from cosmic inflation, the theory that, in the first fraction of a second after the Big Bang, space expanded exponentially faster than light. Inflation explains many observed features of our universe, like its flatness and uniformity. But here's the twist: inflation may be eternal. In this model, once inflation starts, it never completely stops. Quantum fluctuations cause some regions of space to stop inflating, forming bubble universes like ours, while the space between them continues expanding at a furious rate. Each bubble becomes a separate universe, with potentially different physical constants, particles, and even dimensions of space. Crucially, these bubbles are causally disconnected. No signal can cross the inflating void between them. So while they're part of the same quantum field, they're forever isolated. Our universe is just one bubble in an eternally frothing cosmic foam. This version stems from the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. In standard quantum theory, particles exist in superpositions, multiple states at once, until measured, when they collapse into one outcome. But Everett suggested there's no collapse. Instead, every possible quantum outcome actually happens, each in its own branching reality. So when you flip a quantum coin, the universe splits. In one branch you see heads, in another tails. Over time, this creates an ever-growing tree of parallel worlds, trillions upon trillions of versions of history, differing by every possible quantum event. In some, dinosaurs never went extinct. In others, you made a different choice this morning. Unlike the inflationary multiverse, these worlds aren't far away in space. They exist in an abstract Hilbert space, a mathematical realm of quantum states. And while controversial, the many-worlds view avoids the mysterious collapse postulate, making it elegant to some physicists. This idea emerges from string theory, which proposes that fundamental particles are vibrations of tiny, one-dimensional strings. For string theory to work mathematically, it requires 10 or 11 dimensions, far more than the 3 of space and one of time we experience. Where are the extra dimensions? Possibly curled up at microscopic scales, or perhaps our entire universe is a 3D brain, short for membrane, floating in a higher dimensional bulk, like a sheet of paper suspended in a room. Other brains could float nearby, each hosting its own universe with different laws of physics. In this model, gravity might leak into the bulk, which could explain why it's so weak compared to other forces. Even more dramatically, collisions between brains could trigger Big Bangs. Our universe might have been born from such a cosmic crash. Finally, there's the most radical proposal. All mathematically consistent structures exist physically, championed by physicist Max Tegmark. This level 4 multiverse suggests that any universe describable by coherent mathematics is just as real as ours, even if it has 17 dimensions, no time, or entirely alien logic. In this view, physics isn't about discovering the laws of nature. It's about figuring out which mathematical structure we happen to inhabit. Reality isn't made of particles or fields. It is mathematics. Now, let's address the elephant in the room. Is the multiverse even scientific? Critics argue that if other universes are unobservable by definition, the multiverse is untestable and therefore not falsifiable, violating a core principle of science. Nobel laureate David Gross called it a dangerous idea, warning it could halt progress by explaining everything and nothing. But proponents counter that the multiverse is a prediction, not an assumption. Eternal inflation arises from well-tested inflation models. Many worlds solves quantum paradoxes without adding new rules. String theory, while unproven, is a serious attempt at quantum gravity. If these theories are correct, the multiverse follows naturally, even if we can't see it directly. Moreover, scientists look for indirect evidence. For example, a collision between our bubble universe and another might leave a bruise in the cosmic microwave background, a cold or hot spot with unusual symmetry. Teams have searched, none confirmed. Gravitational wave from the early universe could reveal details about inflation, supporting or undermining eternal models. Unexpected patterns in particle physics might hint at extra dimensions or brain effects. So far, no smoking gun. But absence of evidence isn't evidence of absence, especially when the phenomena lie beyond our cosmic horizon. Philosophically, the multiverse also reshapes how we view fine-tuning. Our universe seems improbably perfect for life. If gravity were slightly stronger, stars would burn too fast. If the cosmological constant were larger, galaxies couldn't form. Some see this as evidence of design. But in a multiverse with countless random variations, it's no surprise we find ourselves in a rare life-friendly bubble. It's like winning the lottery. If enough people play, someone has to win. Of course, the multiverse doesn't disprove God or meaning. It simply offers a naturalistic explanation for apparent fine-tuning. For centuries, humanity believed Earth was the center of existence. Then we learned we orbit an ordinary star. Then we discovered our galaxy is just one among trillions. Now, some of the most respected physicists in the world propose an even more radical idea. Our entire universe might be just one of countless others, part of a vast, possibly infinite multiverse. But what does that really mean? And is it science or speculation? Let's begin by clarifying, multiverse isn't a single theory. It's a collection of distinct concepts that arise naturally from well-established physics, though each remains unproven. There are at least 4 major types of multiverses, each born from different lines of reasoning. The most scientifically grounded version comes from cosmic inflation, the theory that, in the first fraction of a second after the Big Bang, space expanded exponentially faster than light. Inflation explains many observed features of our universe, like its flatness and uniformity. But here's the twist. Inflation may be eternal. In this model, once inflation starts, it never completely stops. Quantum fluctuations cause some regions of space to stop inflating, forming bubble universes like ours, while the space between them continues expanding at a furious rate. Each bubble becomes a separate universe, with potentially different physical constants, particles, and even dimensions of space. Crucially, these bubbles are causally disconnected. No signal can cross the inflating void between them. So while they're part of the same quantum field, they're forever isolated. Our universe is just one bubble in an eternally frothing cosmic foam. This version stems from the many worlds interpretation of quantum mechanics, proposed by Hugh Everett in 1957. In standard quantum theory, particles exist in superpositions, multiple states at once, until measured when they collapse into one outcome. But Everett suggested there's no collapse. Instead, every possible quantum outcome actually happens, each in its own branching reality. So when you flip a quantum coin, the universe splits. In one branch you see heads, in another tails. Over time, this creates an ever-growing tree of parallel worlds, trillions upon trillions of versions of history, differing by every possible quantum event. In some, dinosaurs never went extinct. In others, you made a different choice this morning. Unlike the inflationary multiverse, these worlds aren't far away in space. They exist in an abstract Hilbert space, a mathematical realm of quantum states. And while controversial, the many worlds view avoids the mysterious collapse postulate, making it elegant to some physicists. This idea emerges from string theory, which proposes that fundamental particles are vibrations of tiny, one-dimensional strings. For string theory to work mathematically, it requires 10 or 11 dimensions, far more than the 3 of space and 1 at a time we experience. Where are the extra dimensions? Possibly curled up at microscopic scales, or perhaps our entire universe is a 3D brain, short for membrane, floating in a higher dimensional bulk, like a sheet of paper suspended in a room. Other brains could float nearby, each hosting its own universe with different laws of physics. In this model, gravity might leak into the bulk, which could explain why it's so weak compared to other forces. Even more dramatically, collisions between brains could trigger Big Bangs. Our universe might have been born from such a cosmic crash. Finally, there's the most radical proposal. All mathematically consistent structures exist physically. Championed by physicist Max Tegmark, this level 4 multiverse suggests that any universe describable by coherent mathematics is just as real as ours. Even if it has 17 dimensions, no time, or entirely alien logic. In this view, physics isn't about discovering the laws of nature. It's about figuring out which mathematical structure we happen to inhabit. Reality isn't made of particles or fields. It is mathematics. Now, let's address the elephant in the room. Is the multiverse even scientific? Critics argue that if other universes are unobservable by definition, the multiverse is untestable and therefore not falsifiable, violating a core principle of science. Nobel laureate David Gross called it a dangerous idea, warning it could halt progress by explaining everything and nothing. But proponents counter that the multiverse is a prediction, not an assumption. Eternal inflation arises from well-tested inflation models. Many worlds solves quantum paradoxes without adding new rules. String theory, while unproven, is a serious attempt at quantum gravity. If these theories are correct, the multiverse follows naturally, even if we can't see it directly. Moreover, scientists look for indirect evidence. For example, a collision between our bubble universe and another might leave a bruise in the cosmic microwave background, a cold or hot spot with unusual symmetry. Teams have searched, none confirmed. Gravitational wave from the early universe could reveal details about inflation, supporting or undermining eternal models. Unexpected patterns in particle physics might hint at extra dimensions or brain effects. So far, no smoking gun. But absence of evidence isn't evidence of absence, especially when the phenomena lie beyond our cosmic horizon. Philosophically, the multiverse also reshapes how we view fine-tuning. Our universe seems improbably perfect for life. If gravity were slightly stronger, stars would burn too fast. If the cosmological constant were larger, galaxies couldn't form. Some see this as evidence of design. But in a multiverse with countless random variations, it's no surprise we find ourselves in a rare life-friendly bubble. It's like winning the lottery. If enough people play, someone has to win. Of course, the multiverse doesn't disprove God or meaning. It simply offers a naturalistic explanation for apparent fine-tuning. Picture an infinite ocean of boiling water. Bubbles constantly form, expand, and pop, each a fleeting pocket of vapor in a churning sea. Now imagine that instead of water, this ocean is made of quantum fields, and instead of steam, each bubble is an entire universe, complete with galaxies, stars, planets, and perhaps even life. This is the essence of the bubble universe theory, one of the most compelling and mind-bending consequences of modern cosmology, also known as the eternal inflation multiverse. This model suggests our universe is just one bubble among countless others in a vast, ever-expanding cosmic foam. And far from being science fiction, this idea emerges naturally from our best theories about the birth of the cosmos. To understand it, we must return to cosmic inflation, the theory that a fraction of a second after the Big Bang, space underwent a phase of exponential expansion, growing faster than the speed of light. Inflation elegantly explains why the universe is so uniform on large scales, why it appears geometrically flat, and why there are no magnetic monopoles. Observations of the cosmic microwave background strongly support this picture. But here's where it gets extraordinary. Inflation may never truly end. According to the theory of eternal inflation, proposed by physicist Alan Guth and later refined by Andre Linde, the quantum field driving inflation, the inflaton, doesn't decay uniformly across space. Due to quantum fluctuations, some regions stop inflating and cool down, forming hot, dense universes like ours. But in between, space continues inflating at a staggering rate, pushing these newborn universes apart faster than light. Because inflation accelerates, the volume of inflating space grows faster than the volume converting into normal universes. The result? Inflation becomes eternal into the future, endlessly spawning new bubble universes in a self-reproducing cosmos. Each bubble is causally disconnected from the others. No light, matter, or information can cross the inflating void between them. From inside any single bubble, the rest of the multiverse is invisible, unreachable, and unknowable. Yet mathematically, they all coexist within the same quantum field. Now, what makes each bubble unique? Crucially, the laws of physics inside each bubble may differ. During the transition from inflation to a hot Big Bang, the inflating field settles into a stable energy state, a process called symmetry breaking. But like a ball rolling down a complex landscape of hills and valleys, it might settle into different valleys in different bubbles. Each valley corresponds to a different vacuum state, which determines fundamental constants like the strength of gravity, the mass of electrons, or even the number of spatial dimensions. This means some bubbles might have atoms. Others might collapse instantly. Some could support complex chemistry. Others might be filled only with radiation. A tiny fraction, like ours, might be fine-tuned for stars, planets, and life. This offers a powerful explanation for the fine-tuning problem. Why do the constants of nature seem perfectly calibrated for life? In a single universe model, this appears miraculous. But in a multiverse with infinite bubbles, every possible combination of physical laws is realized somewhere. We simply find ourselves in one of the rare habitable pockets, not by design, but by necessity. After all, observers can only exist where conditions allow. Could we ever detect another bubble? In principle, yes, if two bubbles collided before being swept apart by inflation. Such a collision would leave an imprint on the cosmic microwave background, a circular pattern of unusual temperature or polarization, like a bruise on space-time. Teams using data from Planck and other observatories have searched for these signatures. A few candidate anomalies appeared, but none held up under scrutiny. So far, the sky remains silent. Still, the absence of evidence isn't evidence of absence. If collisions are rare, or if they occur beyond our observable horizon, we'd never see them. And even if we did, confirming their origin would be extraordinarily difficult. Critics argue that the bubble universe theory is untestable and therefore unscientific. But proponents counter that it's not an ad hoc hypothesis. It's a direct prediction of well-motivated inflation models that already explain real observations. If inflation is correct, and if quantum fields behave as we think, then eternal inflation and bubble universes follow almost inevitably. Moreover, the theory solves deep puzzles. It explains why our universe began in such a low-entropy, highly ordered state. Each bubble starts fresh, resetting the cosmic clock. It also provides a natural mechanism for generating diversity without invoking supernatural fine-tuning. Philosophically, the bubble multiverse reshapes our cosmic humility. We once thought Earth was the center of creation. Then we learned we orbit an average star in an ordinary galaxy. Now we face the possibility that our entire universe is just one random fluctuation in an infinite metacosmos, a single note in an endless symphony of realities. And yet, within our bubble, the story is still profoundly meaningful. The fact that we're one of countless universes doesn't diminish the wonder of a sunset, the complexity of DNA, or the human quest to understand stars. If anything, it magnifies it. Against infinite odds, in a fleeting pocket of space-time, consciousness arose and began to ask questions. So while we may never visit another bubble or prove their existence beyond doubt, the idea pushes the boundaries of science, philosophy, and imagination. It reminds us that the universe, or multiverse, may be far stranger, richer, and more dynamic than we ever dreamed. And in that endless foam of realities, our little bubble shines not because it's unique, but because it's aware.